In the previous lecture, we studied about the post-correspondence problem, and we saw what the post-correspondence problem is. And we also said that the post-correspondence problem is undecidable, but we did not prove it. Now, in this lecture, we will see the undecidability of the post-correspondence problem, and we will see how we can prove that this post-correspondence problem, or PCP, is undecidable. Alright, so let's see how we can do this. So in order to prove this, here is the approach that we are going to follow. We will take a problem that is already proven to be undecidable and try to convert it to PCP. If we can successfully convert it to an equivalent PCP, then we prove that PCP is also undecidable. So this is a different kind of proof that we are going to follow, and this is proof by reduction. So what we are going to do is we are going to take a problem which we already know is undecidable, and we are going to try to reduce that problem into a PCP. That means we are going to convert that problem into a PCP. And if you are able to successfully convert that problem to a PCP, then we can say that PCP is also undecidable, because the problem that we are taking is already an undecidable problem, and if we can convert it to PCP, that means PCP is also undecidable. So here is what we can do. We can take this problem, which is the acceptance problem of a Turing machine, and we know that this is an undecidable problem. Why? Because we have already discussed about this. We know that we can never be sure if a Turing machine will always go into an accept state or not. We have already discussed and studied about this. So the acceptance problem of a Turing machine is an undecidable problem. We know that. Now, if we can convert this acceptance problem of a Turing machine into a PCP, which we call modified PCP or MPCP, then we can say that PCP is also undecidable. So in order to do this, let us take an example of a Turing machine and let us see if we can convert it to a PCP. So here we have a Turing machine which has three states, Q0, Q1 and Q2, where Q0 is the starting state and Q2 is the final state or the accepting state. And here we have inputs A and B, and then we have tape symbols A, B, X and the blank symbol. So here what happens is that in state Q0, if you get the input A, we replace that A with an X and we move to the right. And then in state Q1, if you get the input B, then we replace the B with an X and we move to the left. And then we reach the final state Q2. So basically, if you get the input of this form AB, we are replacing it with XX, and then we go to the final state. So that is what this Turing machine is doing. So this is the input symbols and these are the tape symbols. And here I have a big letter B or a capital letter B, which denotes the blank symbol. So in some of our other lectures, we wrote this like this. So it means the same thing. All right. Now, let's say that we are taking the input A, B, A. Now we see that in this we have A and B. So A, B. So we know that this is going to reach the accepting state Q2. Now we want to see if we can convert this whole thing into a post-correspondence problem. We will try to reduce it, and we will see what are the steps we need to follow in order to reduce it to a post-correspondence problem, and then we will try to solve that post-correspondence problem. So this is going to be a bit long, but by the end of this you will understand that PCP is undecidable. So first of all, we know that in PCP we have dominoes or set of dominoes, which I have already discussed in the previous lecture, and we know that we should always start with a domino in which the first symbol on top and the first symbol at the bottom is the same. So here I will say that we have a domino called hash hash. We have hash in the numerator and hash in the denominator. So this is how we are going to start off. Now there are 7 steps that we have to follow in order to convert this Turing machine into a post-correspondence problem. So we will discuss step by step, starting with step number 1. So in step 1, what we are going to do is we are going to look at the input symbols that we have, which is A, B, A. So in the tape of our Turing machine, we have this input symbol A, B and A. And in the beginning, we are at this first input A in the tape, and we are at state Q0, which is the starting state. Alright, so this is the status of our tape. And I taught you in one of the lectures about the configuration. How can we write the configuration of a particular instance of a tape in the Turing machine. So if you have not watched that lecture, I will leave the link in the description. You can watch that lecture to find out what is configuration. So I'll not be explaining configuration again. So in configuration, we will write the state and then the inputs. So we'll write it in such a way that we will understand where is the tape head pointing and in which state we are and what are the current inputs we have in the tape. So in this we can write like this. Our state is Q0 and the inputs we have is A, B and A. A, B and A. It is written like this because when we have input A, our tape head is over here and we are in state Q0. So that is why we have Q0, A, B, A. So this is how we write the configuration. Now we need to make dominoes of this form. We will have a hash followed by hash Q0 W, and W represents the input. So if we make the domino for this step 1, it will look something like this. So we have the hash symbol on top and then we have hash here and Q0 W. And this is what we are going to write, Q0 A, B, A. W represents this A, B, A. A, B, A. So this is the first domino that we are creating in step 1. Alright, now let's see what is step number 2. So in step 2, what we are going to do is we are going to make dominoes for the right transitions that we have in our Turing machine. So if we look at our Turing machine, we have two transitions, this one and this one, and this is the only right transition that we have. That means when we move to the right. So if we want to make the right transition, this is how I will write it. I'll write del Q0 A. This means that in Q0, when I get the input A, what happens? We move to state Q1, replacing the A with an X and moving to the right. So we move to state Q1, replacing A with X and moving to the right. So this is what we are doing. Now let us see how does our tape look like in this instance. So let's say this is the tape we have and we have the symbol A encountered in the tape. And when we encounter this symbol A, we are in state Q0, this state Q0. And then what happens is after we take the transition, we replace that A with X and we move to the right and we come to state Q1. So this state Q1, we come to state Q1. So this is how the tape looks like. Now if you want to write the configuration for this, let's see how we can write this. So this can be written as Q0 A because we are at state Q0 pointing at A, and this one we can write it as X Q1. Alright, so again, if you don't know the configuration, you better watch the video where I have discussed about configuration. Links in the description. Now if you form the domino for this step 2, this will be your numerator or the top part, this will be the bottom part. So it can be written as Q0 A by X Q1. So this is the domino from step number 2. Alright, so let us now go to step number 3. So in step 3, I guess you already guessed what we are going to do in step 3. Here we already made the dominoes for the right transition. So in step 3, we are going to look at the left side transitions of our Turing machine. So if you come back and look at the Turing machine that we have, this is the only left transition that we have. From state Q1, if we get input B, we replace B with X and move to the left and come to the final state or the accepting state Q2. So I can write it like this, del from state Q1, if you get the input B, what happens is we go to state Q2 and we replace the B with an X and we move to the left. So this is what happens. Now let's see how does the tape looks like in this instance. So let's say this is the tape and we encountered B, and then when we encounter this B, we are in state Q1. So here what happens is we replace that B with an X and then we move to the left and we are in state Q2. So we have to move to the left now. So I will be on my left and we are at state Q2. So this is what happens in our tape for step 3, where we are looking at the transitions taken to the left. Now if you try to write the instantaneous description or the configuration for this, we cannot write it simply as we wrote for the right side transitions. And why is that? That is because when you move to the left over here, we know that there is going to be some other symbol present here which we do not know what it is. Alright, there can be some other symbols which is already there in the tape to the left. So we have to consider that something is already here. So what I will do is I will write y over here considering the other thing that can be there. So here also I will write y. Now y is not a particular symbol, but it is a generalized way of writing, and y, it belongs to our tape symbols. And what is our tape symbols? We already know our tape symbols contains the symbols A, B, X and the blank symbol. So y can be any of these. Now since y can be any of these, you have to form dominoes for all the conditions when y takes any of these values. So there can be many possibilities. So you have to write down all the possibilities. So let's see what are the dominoes that we can have in this step 3. So let me write the instantaneous description or the configuration here. This one can be written as y q1b, and this will be written as q2 y and x. Alright, this is the way we write it. Now let's see how can we form the dominoes out of this. So as I told you, this y can be any of these values. So we have to consider all the options. So let's say that if y takes the value a, then this will be a q1b. A q1b by, this will be the denominator. So here also y has to be replaced by a. So q2 ax. So this will be one of the dominoes that you can have. Now another possibility is if y takes the value b. So it will be b q1b by q2bx. Alright, so this is another one. And then another possibility is if it takes the value x. If y takes the value x. So it will be x q1b by q2. This y will be replaced by x, and this x again x. So this is another domino. And the other possibility is if y takes the blank symbol. So it will be capital B q1b by q2bx. So these are the dominoes that can be formed from step number 3. These are all the possibilities that we have. Alright, now let's go to step number 4. So in this step number 4, what we are going to have is, we are going to have dominoes for all the possible tape symbols. All possible tape symbols. And we know what are the tape symbols that we have. They are tau is equal to A, B, X and the blank symbol capital B. Now we have to form dominoes for all these tape symbols. And how do we form it? This is the way we form it. For A, we form a domino called AA, and then for B, we form a domino called BB, and then for X, we form a domino XX, and then for the blank symbol, we form a domino capital B, capital B. So this is your step number 4. Now in step 5, we are going to have dominoes for all possible tape symbols after reaching the accepting state. And what is our accepting state that we have in our Turing machine? It was state Q2. We already saw that state Q2 was the accepting state in our Turing machine. So how do we form dominoes for all the tape symbols after reaching the accept state? So our tape symbols are A, B, X and B. So let's take for A first. We will write like this: A Q2 by Q2. This is one possibility. And also we can have Q2A by Q2. So when you consider the input symbol A, when it reaches the final state Q2, these are the two possible dominoes that you can have. So similarly for the tape symbol B, you can have B Q2 by Q2, and then you can have Q2B by Q2. So this is for tape symbol B, and then we have X. So for X we can have X Q2 by Q2, and then we can have Q2X by Q2. So Q2 is our accepting state, and then we have the blank symbol we have to make for that one also. So we can have B Q2 by Q2, and then Q2B by Q2. So these are the symbols you can have for all possible tape symbols after they reach the accepting state, which is Q2. So in step number 6, we are going to form a domino for the blank symbol and also for the hash symbol. So the hash symbol, which I told you in the beginning, hash hash, this is one domino that we are going to have in step 6. And then for the blank symbol, we'll have a domino like this, hash by blank hash. So this is the procedure you have to follow, and you have to make dominoes like this. Now for the last step, which is step number 7, you are going to make domino for the final state or the accepting state. So which is our final state? Our final state is Q2. So we will make a domino like this, Q2 hash by, Q2 hash hash by hash. So you have to make a domino like this. So now we have completed the 7 steps in converting the Turing machine to set of dominoes for the PCP. So if you look, these are the dominoes that we have in this yellow kind of color that I have written. These are the dominoes, 1, 2, and here we have 4, here we have 4, and here we have 1, 2, 3, 4, 5, 6, 7, 8, and here we have 2, and here we have 1. So these are the set of dominoes we have, and using this set of dominoes, we will try to see if we can find a solution to this PCP. So we have converted the Turing machine to PCP, we have our set of dominoes, and in the previous lecture I already showed you how we solve our PCP. So using the same concept, we'll see if we can solve this PCP or not. So now let us try to find a solution to our PCP using the dominoes that we have obtained. Now I already taught you in the previous lecture how to solve it, and the first step in solving is we need to find a domino in which the top symbol and the bottom symbol in the beginning are the same. So if you look at the set of dominoes that we have in step 1, hash by hash Q0 ABA. Oh, and here there should be another hash which I missed out. I'm sorry about this. So there is another hash over here. So just note this point. So we can start with this domino because we have hash in the top beginning and hash at the bottom beginning. So I'll be starting with this domino, hash by hash Q0 ABA hash. So this will be the first domino that we can use for our solution. Let me write it here. Hash by hash Q0 ABA hash. So this is the first domino that we have. Now we know that in solving a PCP using these dominoes, our aim is to match the top and the bottom. So if you look here, on top we have hash and on the bottom we have hash Q0 ABA hash. So this Q0 ABA hash is the extra thing that we do not have in the numerator or the top part. So we need to find a domino which can provide us this in the top part. So let us see in our set of dominoes that we have, and if you look at step number 2, you see a domino which has Q0 A on top. So Q0 A by X Q1. So I can use this in our solution because this Q0 A will be matched or cancelled out if I use that. So let me use that. Q0 A by X Q1. So this is what we get from step number 2. Now if you see, hash Q0 A, hash Q0 A will be matched. Now the extra thing that we have is this B and A and hash. So for this we need to find something that can cancel this B and A from the numerator part. So let's see if we have something like that. Yes, in step 4 we have BB, so B is there on top, and here we have AA, A is there on top. So I can put that in our solution. So I can use B by B so that this B will be cancelled out, and for this A I can use A by A. So this is what I can use. Now what is extra? Hash is there. So in order to cancel hash, we have hash hash domino, which I already showed you in the 6th step. Actually we created this hash hash domino. Now we have this. Now let's see if it is matching or not. So this hash and hash will be cancelled, and this Q0 and Q0 is cancelled, this A and A is cancelled, this B and B is cancelled, this A and A is also cancelled, and this hash and hash also can be cancelled, but I will just leave it to be written down to the next step. Now let me write down the remaining things to the next step. So here I have a hash, so I have hash over here, on top only hash is there, and then in the denominator we have hash, this hash X Q1BA, X Q1BA, and this hash. So this is what we have remaining, and we need to find some other dominoes in order to match these symbols. This hash hash can be cancelled, and then we have xq1ba. Now we need to find out something which can give us this sequence xq1ba on top. Now again, if you look at the set of dominoes that we created in step 3, we have this xq1b by q2xx. So this xq1b can be used to cancel out what we were having there. So let me use this particular domino in our solution. So it was xq1b by q2xx. So this is from step number 3, the dominoes that we obtained in step number 3. Now we see that xq1b is cancelled, and then this a is the extra thing. So we can use the aa domino that we have to cancel out that a from here, and then we have an extra hash. So to cancel out that hash, I can use the hash hash domino. Alright, so this is what we have now, and let's see, this hash and hash is cancelled, this x and x is cancelled, q1 is gone, b gone, a and a is gone, and then this hash hash will be cancelled, which I'll do in the next step. So let me write down what are the remaining things we have. We have hash on top, nothing else on top. Then we have hash again. Then q2xxa, and then this hash. So this is what we have now, and we need to find a solution, or we need to find a set of dominoes matching this. So this hash and hash can be cancelled. Now we have q2xx. Now we need to find something that will give me this sequence q2xxa. So let us go and look in our set of dominoes. So if you look at step 5, you have q2x by q2. So the q2x can be used to cancel out the q2x that we have over here. So let me use that domino from step number 5, which is q2x by q2. Alright, so if I use this q2x and this q2x will be matched and cancelled. Now we have x, a, and then hash. So in order to cancel this x, we can use the xx domino, which we have from step number 4. And then we can cancel this a using the aa domino, again from step number 4. And then we can use hash hash domino to cancel that hash we have over there. Now let's see what will be cancelled out. So q2 and q2 is cancelled, x and x is cancelled, this x and this x is cancelled, this a and a is cancelled, and this hash hash, I will write them down and then cancel it. So let us write down. On top we have this hash, and then on the bottom we have hash here, and then what is the extra thing? q2xa hash. q2xa hash. So this is what we have now. And now if you look again, q2x, okay, this hash hash will be cancelled, then q2xa. So we need to find something that can cancel q2x. So we can use the same domino that we used before from step number 5, q2x. q2x by, what was it? q2. Alright, now this q2x will be cancelled. Then we have a and then hash. So for a, I will use the aa domino, and for hash, I will use the hash hash domino. And now let's see what are the things that will be cancelled out. Hash hash is already cancelled, q2 gone, x and x is cancelled, a and a is cancelled, and this hash and hash, I will cancel it in the next step. So let's write down what are the things that we have. We have hash on top, and on the bottom we have hash q2a hash. q2a hash. Alright. Now you may be thinking, why am I always cancelling that extra hash in the next step? You can cancel it even in the previous step, but what will happen is that if you cancel it, then in the next step when I write it down, there will be nothing on the numerator, and that does not look nice. So just for that I am doing it. There is no particular reason other than that. You can cancel it if you like. And now coming to this, we have this hash hash which can be cancelled. Then you have q2a. Now for this q2a hash, what is the domino that we can find out? So from step 5, you see we have q2a by q2. So I can use that q2a by q2 from step number 5. So it will be q2a by q2 from step number 5. And then q2a will be cancelled, and for this hash, I will use the hash by hash domino to cancel out that hash. Now let's see what all will be cancelled out. Hash hash is gone, q2 and q2 gone, a and a will be gone, and now this hash I will leave it for the next step. So let me write down what are the things we have now. We have hash, this one, and then we have hash q2 hash, hash q2 hash. Now this is the next domino that we have. Now in order to cancel this, if you look at step 7, you have q2 hash hash by hash. So this is the perfect domino that you can use in order to cancel out this one. So q2 hash hash by hash. So this is from step number 7. Now if you look, hash and hash will be cancelled, q2 and q2 is cancelled, hash and hash is cancelled, and hash and hash is cancelled. So we see that everything is cancelled. Now if everything is cancelled means the top part and the bottom part are exactly matched now. So if we found a match for the top and the bottom, that means this PCP is solved. That means we found the solution to this PCP. So we saw that this PCP was formed from the Turing machine. We had the Turing machine in the beginning. Where is it? This is our Turing machine, and we saw that this Turing machine was going to an accepting state when we gave this input ABA, and we converted this into a PCP, and we found that for that same input, the PCP also, when we converted it into a set of dominoes, we are able to find a solution to that PCP. So we found that we could exactly convert our Turing machine, or we could reduce our Turing machine to a post correspondence problem. So now I can say that this PCP is undecidable. Now why is that? That is because we converted this PCP from the Turing machine, and what we were looking at was the acceptance problem of the Turing machine, and we know already that the acceptance problem of Turing machine is an undecidable problem. So since we could convert that acceptance problem of Turing machine to a PCP, and since we found that it has a solution, then it shows that this PCP also is undecidable. So hence we have proved that PCP is undecidable. So let us go and take a look at our approach that we had in the beginning. We wanted to convert the acceptance problem of a Turing machine to a PCP. And if we could do it successfully, then we can say that PCP is also undecidable, and that is what we just did now. Hence, we have proved that PCP is an undecidable problem. So I hope this was clear to you. Thank you for watching, and see you in the next one.